Bridgelux LED Arrays. Bridgelux. Welcome to this training module on Bridgelux LED Arrays. This training module introduces Bridgelux LED Array products and application considerations. The Bridgelux family of LED array products provide high-performance, compact, and cost-effective light sources for solid-state lighting. The Bridgelux LED arrays have been specifically developed to provide lamp and luminaire manufacturers with a solution that will simplify system-level integration, further reducing the system cost. These products combine the higher efficiency, lifetime, and reliability benefits of LEDs with the light output levels of many conventional lighting sources. Product options are tailored to match light output levels of conventional light sources, delivering between 400 and 2000 lumens under application conditions in cool, neutral, and warm white colors. In order to satisfy system design requirements, the Bridgelux LED arrays are specified to deliver these values hot or under assumed typical use conditions, eliminating the need for incorporating additional sources to account for thermal degradation. Various configurations are available, allowing the product to be optimized on efficacy, CRI, light output, cost, or a combination of these attributes. These high lumen output integrated sources reduce system design complexity, enabling miniaturized, cost-effective lamp and luminaire designs. Typical applications include task, accent, spot, track, downlight, wide area, and security lighting. This explains the part number designation for Bridgelux LED arrays. The base product part number, BXRA-ABCDE, is indicated on each individual unit, printed on the bottom of the array. Here lists lamp equivalents for available lumen options in this LED array family based on average conventional lamp performance. You may select suitable LED array products based on the application requirements from this table. The first parameter considered is lumens, which expresses the total quantity of light given off by the LED. Color temperature is a characteristic of visible light. Higher color temperatures are cool colors, and lower color temperatures are warm colors. Cool colored light is considered better for visual tasks, and warm colored light is preferred for living space. The next parameter considered is Color Rendering Index, or CRI, which indicates measure of the degree of color shift an object undergoes when illuminated by a light source as compared to a reference source of the same color temperature. A higher value represents less color distortion, or a more accurate color. Natural daylight is rated 100. In lighting design, efficacy refers to the amount of light produced by an LED as the ratio of the amount of energy. This parameter will influence the efficacy of the whole lighting system. Through LED datasheets, several performance characteristics of the LED array products, including flux, forward voltage, color, and reliability, are dependent upon temperature. As temperature increases, several performance parameters experience a temporary and recoverable shift. With increasing temperature, light output, or flux, decreases, forward voltage decreases, and the color temperature shifts towards blue. Furthermore, absolute maximum ratings, such as maximum case temperature and maximum junction temperature, must not be exceeded. Exceeding the absolute maximum ratings, as listed in the product datasheet, may irreversibly damage the product and cause permanent shifts in performance. Therefore, optimization of performance and reliability in a lighting system using Bridgelux LED arrays requires proper thermal management. When voltage is applied across the junction of an LED, current flows through the junction generating light. It is a common misconception that LEDs do not generate heat. While essentially no heat is generated in the light beam, unlike conventional light sources, heat is generated at the case of the LED array and must be effectively managed. As LEDs are not 100% efficient at converting input power to light, some of the energy is converted into heat and must be transferred to the ambient. Heat generated by additional sources, such as a power supply located near the LED, must also be managed. In order to reduce the size and cost of the thermal management solution, and to minimize the output of additional heat added to the system, power supplies and other heat-generating components should be located in close proximity to the LED array. Heat generated at the LED junction must be transferred to the ambient via all elements that make up the thermal management solution. These elements include the LED array, the thermal interface material used between the LED array and heatsink, the heatsink, the luminaire enclosure, if applicable, and other components that come into contact with the lighting assembly. Here shows a simple thermal mode for a single LED array mounted to a heatsink. The figure illustrates the heat flowing through an LED array. There are many commercially available components, including heat sinks and heat pipes, which may be used with the Bridgelux LED array products. The most commonly used components are heat sinks, typically made of aluminum or copper. Heat sinks conduct heat from a heat source and then convect the heat to the ambient. The size of the required heat sink depends on many variables, including the temperature requirements for the application, the material of the heat sink, the surface characteristics of the heat sink, and the physical constraints for the application. To ensure heat flow from the LED array to a heat sink, pay close attention to air gaps or voids located between the bottom of the LED array and the heat sink. Such voids will significantly impede the flow of heat and therefore must be eliminated. The use of thermal interface materials such as thermal greases, pastes, or adhesives is recommended to ensure that air gaps and voids are eliminated. Assembly requirements for a lighting system using a Bridgelux LED array are listed. The figure shows a reference assembly of a lighting system. Components of the lighting system include wires, solder, screws, lock washers, flat washers, heat sink, and a thermal interface material in addition to the LED array. For some applications, secondary optics such as reflectors, columnators, or other lens systems may be required to direct the light. A thin layer of thermal grease should be applied to the bottom surface of the array, between the bottom of the array and the heatsink. All air gaps and voids between the heatsink and the array should be eliminated. Ensure that sufficient thermal grease is used to cover the entire bottom surface of the array, but not so much that the grease creeps up to the front of the array.